All right, I think it's working. All right, so we have this. If we exponent, okay, so this is g plus. Okay, so we'll take a look at how this works. And oh, I'm sorry, this is beyond. So this, the red line g plus. This is our envelope distribution. We propose values from here, right? So this is, it's still still a form of rejection sampling. Okay, and so the way rejection sampling works is we, let me copy this onto the next slide. So the way rejection sampling works is we propose values from our envelope distribution, okay? And the only requirement is that the envelope distribution has to be taller than the actual distribution. So this is our envelope distribution. And we use this to propose values, okay? And basically, if we propose a value, we then compute the ratio between the height of our envelope distribution and the actual distribution of interest. Okay, so if we, let's say we propose a value right here. Okay, this gets proposed. So we calculate what proportion of this height is covered by the actual PDF, right? So our, we propose, we'll call this y1. We propose y1, and then we find the ratio between the PDF of the actual thing. Maybe I'll use the PDF at y1, okay, which is black. This height divided by the height of the envelope distribution at y1. Okay, and we will accept this value if a new uniform is smaller than this ratio. Okay, so we generate u, and if u is less than or equal to the ratio, we accept y1 as a sample from the PDF, from the actual PDF. Okay. If later on we propose, let's say right here, y2, we calculate this ratio between this height, the height of the envelope distribution, and the height of the actual PDF. Okay, so we find ratio. So, this one has a high chance of getting accepted, right? Because this is like 80% of the height here. This one has a lower chance because maybe it looks only like 65% or something. Okay, so the ratio again, height of the PDF divided by height of the envelope distribution. Okay. And then if it's rejected, and so this would just be regular old acceptance rejection sampling, okay? But this is where the adaptive part comes in. If this is rejected, okay, we will use this as this proposed location as a new tangent line, okay? If this is rejected, we will use the proposed value as a new point, as a new grid point to find our tangent lines. Okay, and so this becomes a new kind of a grid point, and so what happens is that, you know, we go back to the, if we look at the log PDF, we're going to have something. We have this thing, and it used to be just these 2 points, but now we're going to include this. This is the new point. And we calculate the tangent lines based off of this new point, which go from there to there to there or something. And thus, you know, when we exponentiate kind of h plus, you know, the PDF looks like this, and our I don't know, our proposal envelope will probably look something like this. This is like a crude representation. And so I have some just very crude code that does kind of this job here, and we can try it out. And there's one part of the code which is really bad. But yeah, it kind of works. Okay, so I'm going to just set some min and max. This is h of x. This is the log of the PDF. So here I just have an upside down parabola, y squared negative y squared. And then the derivative of my upside down parabola is negative 2 times y. And that's used so we can find tangent lines, right? We need the derivative to find the slope of the tangent lines. And then, you know, basically, you got to find the intersection points. And so if you use point slope form, then the equation at, you know, one tangent line is this, and the equation of the other tangent line is this, you know, y minus y1 times the slope times x minus x1, or in this case h minus h1 is equal to the slope times y minus, you know, y1. And then if we solve for where they equal each other, this is what you'll get as far as the intersections. And so this is how we can find the intersections. So here, let me just kind of demonstrate this. If I say my fixed points are negative 2 and 2, and I plot this, this is what the log of the PDF looks like. And these are, maybe I'll make this larger. I don't know if that's any better. These are going to be my fixed points, and if I ask, you know, what is the intersection? Well, when I run the intersection of these fixed points, it says these two tangent lines will intersect at 0. Okay, and so this function h plus, what it does is it says, okay, if the intersection is at 0, then everything lower than 0 is going to belong to the first line segment. Everything greater than 0 belongs to the second line segment. Okay, and so it uses the find interval to kind of assign, you know, these values of y because I have basically a vector of y values that go from -3 to +3. And it says these values of y go from, from -3 up to 0 will belong to the first line segment. From 0 to 3 will belong to the second line segment. And then it just finds the equation of that line segment by just saying, we know the slope because we have the derivative formula. So we can find the slope, and we just say, find the equation of the line that with this slope and runs through this point. And so we can plot that, and we can say this is what the tangent line looks like there. Okay. If I used a different set of fixed points, this is what the thing would look like here. Okay. But here, let's just go back and we'll use these fixed points. All right. Okay. This is the part of the code that's really bad. But what we're going to do now is we're going to turn this into, we're going to exponentiate it. Okay, so I'm going to take this red line and I'm going to exponentiate the red line. So my red line is represented by h plus of y with the fixed points. And so I can plot what that looks like. So this is the actual thing, and it's so tall that the normal curve is really short here. Okay, but if I just change my y limits to something more reasonable, from let's say 0 to 3, okay, we can see it shoots up, and this is the normal curve in here. Okay, so it's gonna this is gonna propose, if any value in here gets proposed, it's gonna get rejected, right? I mean, there's a chance that it gets accepted, but there's a quite a high likelihood of getting rejected, and that's because we're exponentiating this thing. So with exponents, the gap here is actually quite significant. Okay, so anyway, what this G plus CDF does is it takes this thing, so the envelope distribution, it's going to integrate this. It's going to find the integral of this. Now I'm using R's function integrate to do this. Okay, it's integrating this function, which is the exponent of the linear PDF, or I guess I can just call this G plus. That's actually probably better. Okay, I'll call this G plus. Okay, and so yeah, we're exponentiating h plus to get our G plus, and we're going to just integrate it from negative. In this case, we go from -infinity to the value that we're looking at. Okay, and I'm using R's function integrate. It wouldn't be too terrible. It would be. It's a bit of a. It is a slightly daunting programming task, but it's also, as far as the math goes, the math is not too terrible, right? Because when you integrate e of the x, you just get e to the x, right? So plus a constant. And that's basically what the author of the original code writes, except it gets a little hairy, because you've got to say up to a certain point it's this, and then once it's in the next interval, you have to take whatever value this was, and you do the definite integral from this cut point, intersection point, to the spot that you're looking at. Okay. I just said, we're going to just use integrate and cheat. Okay, and so so this is kind of what it looks like, and we can compare the CDF. This is the CDF of my G plus, my approximation, and this is the true CDF. So we can see there's some serious deficiencies at this point, right? And there's a huge gap between the actual PDF and what we're proposing here. Okay, So this is the part where I'm a little bit embarrassed by, but it kind of works. So what I'm going to do is using this is kind of my inverse CDF. This black line is the inverse CDF of my G plus, my approximation. And so I'm going to just propose a value using our unit form, okay, and this is U. I get 0.95, and I'm going to just go from 0.95, I'm going to come over here, and I'm going to map it to a value here, okay? And so, well, I should probably go back and try to find a better way to do this, but I'm just saying find the closest value and map it over, okay? So I'm just saying, you know, I have my CDF, which is what I use to plot this, and I'm going to say find the CDF value, you know, subtract my proposed U, and find the one that has the smallest absolute distance from there, okay? And so according to this, when I look up 0.951, the closest proposed value is 0.58. So I can just say AB line V equals to 0.58. That's right here, and this should be close to point whatever my U is. Okay, so that's where we intersected, and that's, so I said the U that I generated is right here, and so when I come across, this translates into 0.58, right? That's inverse transform method. We're going from the CDF to a proposed value. Okay, so my proposed value at this point is 0.58, and then we're going to come back here and we're going to say, all right, generate a new U value. Okay, this is 0.612, and we're going to say, okay, if I go to 0.58, if I come to this plot and I calculate the height of the bar at 0.58, and I divide by, or I find the PDF, the height of the PDF, and I divide by the height of 0.58. So let me just plot this AB line, V equals 0.58. You know, what is the ratio between this height and this location, right? Here, let's just take a closer look here, and well, it's kind of off the charts. We say, you know, what is this? So this ratio is the our PDF, e to the h of our proposed value divided by e to h plus of our proposed value. So if we calculate this, the acceptance ratio is only, it says this is 13% of this height, okay? And so we will accept this only if U2 is smaller than this, okay? But it's not, right? So we're going to reject this value. So if it were smaller, we would accept the proposed as an x, but it's not. So what we're going to do is we're going to take this proposed value of 0.58, my proposed value, and use that as a new grid point. And so my grid points, y fixed, will be, I'm going to combine y fixed with proposed, and I'm going to sort them. Okay, so in this case, we do that. Once I have a new set of grid points, I'm going to recalculate the h plus. Okay, and then we can recalculate the CDF there. Okay, so let me just kind of go back and show you how the again, the piecewise function compares to the, so this is, let's look at the log PDF now. So my log, this is the log of the PDF, the quadratic, but then now I have another grid point of 0.58 here, and so here, this is what my my thing looks like, and comparing this to the thing, this is what our new, this is our envelope distribution. It looks funny, okay, but our envelope distribution, and this is the actual thing that we're trying to approximate. And so we can, you know, we'll calculate, we can use the CDF again. So this is the CDF of this thing. It looks funny, okay? But using this again, we can propose a new U value. And so my proposed value here is going to be 0.39. And AB line B equals 0. Oh, H is equal to, no, B equals 0.39. Okay, that's this is what we have. You know, the U I generated was 0.828, and the closest value associated there is 0.39. And so now we will we'll take a look and we'll see, you know, where does 0.39 fit on here? Okay, so AV line of. Okay, so this is going to get accepted with very high likelihood, right? Because the ratio between here and here, that's gonna be high. So what is, unless U2 is, you know, really high, and so in this case, oops, I guess I don't know if did I mess something up? Maybe I messed something up. All right, now I'm a little nervous about what just happened. Okay, let me. Did this change? No. Okay. So yeah, so everything's stayed the same. All right, this time I'm going to just kind of purposely choose values that I think will get rejected. So I think if I propose, let's say, negative 0.9, okay, so I'm going to say proposed. Instead of proposing them using a random uniform, I'm going to just say negative 0.9. Okay, let's say this gets proposed. And so let's just do let's see where this is. Okay, so the ratio between this height and the actual thing is quite low, so it's probably going to get rejected. And you know what? So I can just kind of see, you know, is this going to get, well, let's generate that again. Okay. One more time. Oh man, it doesn't want me to. Okay, so it'll get rejected if U2 is 0.4419. Okay, so you know, if I calculate the ratio, we'll see. Okay, 0.44 is larger than this, so it's going to get rejected. And it goes through and it calculates the new set of grid points. And so now, if I plot this, it has accepted this as a grid point, and so now our proposal envelope is a lot tighter to the actual distribution here. Okay, and you know, again, looking at the log PDF, we can see kind of all of these different locations that we've proposed, and okay, and so as we continue on, and if things get rejected, they get added to the grid, and so our envelope will get tighter and tighter, and to the point where we're no longer proposing bad values per se. Okay, and so our, you know, our acceptance ratio will get higher and higher, and this could be beneficial depending on what your distribution looks like and how difficult it is to you know, if you're accepting or rejecting a high ratio of numbers. So so adaptive rejection sampling is a tool to kind of get our envelopes tighter and tighter. Okay, I mean, technically, so here we've been using tangent lines of this thing, and technically we could also just set up an arbitrary set of grid points to on the actual PDF with straight lines. The reason why we deal with the log is because when we deal with the log of the PDF, a lot of times you get these nice concave shapes. Okay, you'll have these concave down shapes which make it ideal for trying to fit with tangent lines. Okay, if after taking the log you don't have this concave shape, then this method would fail, because what would happen is, if let's say the thing looks like this, and you create tangent lines, something like this, you're gonna get I don't know, it's not gonna work out as well here. Okay, so well, I don't know, maybe in this case, I'm trying to think, but there could be a point where it's lower, right? And this would be problematic in terms of proposing values. Okay, so when you exponentiate, the envelope always needs to be greater than, and if you're trying to fit something with straight lines and you have something that ends up going in the opposite direction, then this will be a problem. Okay, because these values will not get proposed as often as they should. So that's why we're dealing with the log of the PDF, because for things in the exponential family, so that's like the chi-squared and the normal and a lot of these things, they are log concave. Okay, and so I'm trying to for your next homework, I'm trying to think of a good, interesting problem, but doable as well. So, and that's always a challenge. So, so we'll work on that. Okay. So I just want to talk a little bit about that, and so we'll wrap up here, and we'll see you guys on Monday. So have a great weekend.